Today we're going to be looking at another one of NileRed's videos, specifically making purple gold. Man, that looks like it's radioactive or something. And well, actually, gold is a little bit radioactive, though that's not the reason why it's purple. And going by the length of the original video, this reaction is going to be split up into multiple parts, so please stay tuned for that. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry, from engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's get right into this.
This video has been sponsored by Opera. Back in 2019, I was sent some old jewelry from a viewer, and I was able to turn it into these pure 24-karat gold bars, which I thought were pretty nice.
I remember that video.
Since then, though, I've been really interested in gold in general, and a couple years ago, I stumbled onto a form of it that I'd somehow never heard of before. It was something called purple gold, and this website was selling it as jewelry, and in my opinion, it was one of the nicest forms of gold that I had ever seen. However, the color of it also kind of seemed unnatural, and at first, I honestly thought that it was probably a scam. With very little research, though, I quickly found out that purple gold was actually real,
just a compound.
And according to Wikipedia, it was an alloy of gold and aluminum. Now, I'm not someone who's normally into jewelry,
so not pure
but for
gold.
some reason, the moment that I saw that it was real, I really wanted to buy some.
Now, what's interesting is it is technically possible to make gold in a nuclear reactor, though it's pretty rare, because it's technically possible when you fission a uranium-235, your fission products are not always the same. You'll see the probabilities are mainly centered around atomic masses of 100-ish to about 130. Approximately, which is why you see things like xenon-135 or cesium-137 show up quite a bit, or strontium-90. And gold, well, it's at 197, which you don't even see on this chart, which doesn't mean it's impossible, so you can get it. It'd be a very lopsided fission collision, if you will, with the neutron hitting your uranium or plutonium nucleus. But it is technically possible, but I can't say I recommend using nuclear reactors for large-scale alchemy. Never thought I'd have to say that.
More specifically, though, I really wanted a ring that was made entirely out of purple gold. However, long story short, that website didn't sell one.
It's fascinating.
And as far as I could tell, there wasn't a single company or person in the world who sold a pure purple gold ring.
Maybe I'm a bit more traditional, but hey. Purple could be fun.
At first, I thought this was kind of odd, but apparently this was just because purple gold was a huge pain to make and to work with in general. It also turned out that Lee Wah, the owner of that website, was one of the only companies that even made purple gold jewelry. With all that being said, though, I still really wanted a pure purple gold ring, and now, knowing that it was actually impossible to buy, I kind of wanted it even more. At the same time, I also felt that it had to be possible to make an entire ring out of it, and I started thinking that this was something that I might just be able to make myself. I mean, I had absolutely zero experience with purple gold, and I had never made a ring out of anything before. But for some reason, I really felt that I could do it, and I decided to just go for it.
That is an awesome attitude. I kind of wish I had that sort of mindset.
But anyway, to get started, the first thing that I had to do was figure out how to even make the purple gold. And with a quick Google search, I was able to find a lot of videos and articles talking about it. However, none of them gave any real information
on how to
make anything remotely decent. With a bit more searching, though, I was eventually able to find this patent, which turned out to be extremely useful.
Interesting.
This is because it not only gave a lot of good info about purple gold in general, it also explained how to potentially fix one of the biggest problems with it, which was how fragile it was. It said that normally...
Now that's so weird for it to be that. I guess it's just the alloy with the aluminum causes that thing, because gold is known for being super, super malleable. You could even make radiation shielding out of gold. It's expensive, though it is It's one of the densest. It's 70% denser than lead, so it'd be a great gamma shield.
The typical mixture of about 78.5% gold and 21.5% aluminum, it was as brittle as glass or porcelain, and that it was way too fragile to make any jewelry with it. However, it claimed that by altering its composition just slightly, or by adding some other metals to it, like palladium or nickel, it was possible to make purple gold that was significantly stronger. It also provided a bunch of example recipes, and the one that caught my eye was this one, which appeared to be the simplest. It didn't require any other metals besides gold and aluminum, and the only difference was that the gold content was slightly increased to 81%, which would make it about 19 karat gold, and this was what I decided to go with. The only tricky part was that besides the ingredients, it really didn't tell me anything else, and there was pretty much no information on how to actually make the purple gold.
This is beginning to become a running trope for a NileRed video. It's like, yeah, this thing is sort of possible to do, but we don't really have a documented process to follow, so we're just going to kind of wing it and figure out how to do stuff like that. It actually kind of reminds me of things like the Manhattan Project, because they've never synthesized a nuclear weapon, nuclear device before. Uranium-235 was this exotic super element because all that they had was just natural uranium. In fact, to make the little boy device, they used well over 90% of all the uranium-235 in the world just because there's so little of it back in 1945.
So unfortunately, this meant that I was going to have to figure out everything myself, and considering that it was supposed to be really hard to work with,
it will shatter in the dust. I was honestly
kind of worried.
You cannot pour an ingot or cast this alloy. No, I really want to see a purple ingot. That would be so cool. Like a purple section of Fort Knox.
At the last second, I found out that all of the purple gold that's sold by Li Hua is actually based on this patent. So even though it didn't give any real instructions, I at least knew that the recipe itself should have been trustworthy, and I decided to just go for it. With that being said, I could now actually get started, and the first and most important thing that I needed was some gold.
I like that it's in gold font.
Unfortunately, isn't exactly cheap. So I initially planned on buying as little as possible.
You could do the same thing he did for that other video.
And I figured that something like 20 grams would probably be more than enough.
Get some junk
At the last minute, though, I convinced myself that it was a good idea to get a bit more, just in case I needed it, and long story short, I ended up with this 100-gram bar. In total, this cost me about $5,700 US, or about $7,800 Canadian, and this immediately put me over the budget that I originally had for this project.
The best part is this gold bar came in one of these pain-to-open little container things that I like that he just immediately takes a box cutter and goes right to it, because those things are have always been more trouble than they're worth. But yeah, it's gold, and I've never seen anything gold or really anything that expensive in one of those specific types of containers.
And it was probably way more than I needed, but oh well. Either way, I now had this beautiful and shiny bar of gold.
It almost looks fake.
And just looking at it and holding it in my hand was oddly satisfying. The only sad part was
I've seen in some places the comma referred to as a decimal point, though not on anything I've ever worked with in the nuclear plant or any professional engineering type documentation or reference. I actually think it's a bit confusing because I'm used to seeing comma as in between to count every 3 digits over, like a comma after 1,000, for instance. And seeing a comma with only 1 digit after it, to me, is a little confusing.
That it was kind of useless to me as one big bar, and unfortunately, the first thing that I had to do with it was destroy it.
No, but it's
more
just so
specifically,
pretty.
I was going to have to break it apart into a bunch of smaller pieces because I had to be able to measure out very specific and accurate amounts of it. To do this, the most obvious way would have been to tear it apart manually using something like a chisel and a hammer, but that would have been an insane amount of work with most likely mediocre results. Instead, I felt that it was a much better idea to do it chemically.
There you go.
So I just carefully placed it in a beaker and I poured in a bunch of concentrated hydrochloric acid.
That's big for gold. Well, it's expensive.
I then turned on the heating, and over the next few minutes, it slowly warmed up, and it eventually started boiling. Then, when I felt that I was ready, I shot in some concentrated nitric acid. Almost immediately, there was a lot more bubbling,
There we go.
and the solution
It's turning
started
yellow.
changing color. This is because the nitric acid was reacting with the hydrochloric acid, and it was forming nitrosyl chloride and chlorine gas, both of which are yellow.
Yeah, better have your fume
More
hood ready.
importantly, though, unlike the hydrochloric
gas.
acid alone, this new acid mixture, commonly known as aqua regia, was able to attack the gold bar. It wasn't super fast, but it was slowly shredding it apart, and it was turning it into something called chloroauric acid, which was then getting dissolved away.
This is a fun thing. I've never heard of, chloroauric. That's a fun word to say, but that's awesome.
So, what I was doing here was...
It's just fascinating how you can just separate stuff out like that, down to the micro and nano level. Speaking of which, gold can actually be used for medical imaging in certain diagnostic procedures, like CT scans, for instance, because it enhances the contrast on X-ray images in the CT scans, because gold has a high absorption cross-section. When I say cross-section, I mean it has a high probability of absorbing X-rays. So when it's inserted into the body on, again, a nanoparticle form, don't recommend inserting this acid or just having someone swallow a gold bar. That would be expensive. Then again, everything is expensive that's healthcare related, at least in the US. But anyway, it'll help things be easier to spot in certain tissues just because of that added contrast that gold would provide to your X-ray imagings. They can also even be targeted to accumulate in tumors, which would help you just find where the cancer is and where it's spreading. So gold can be a medical device, which is fascinating.
Basically breaking it apart at the atomic level, which was way better than I could ever do manually. And on top of that...
manually. There's a bunch of industry jokes that people who have been in the nuclear industry for a long time, that back in their day, they split atoms with really, really small hammers. That'd be kind of hard to do.
It was just a lot easier. All I had to do was occasionally add small amounts of nitric acid,
Now
and
it's
over the
turning
next
orange.
few hours, it
Now red.
very slowly disappeared. Eventually, all that was left was just a thin sheet of gold,
Whoa.
and with just a little bit more acid, I was able to completely get rid of it.
Now we
There
got
was
some
now
expensive
absolutely
gold
no
drink.
trace of the original bar, and all 100 grams of the gold was dissolved as the chloroauric acid.
What's interesting is gold in the nanoparticle form that you see for diagnostic aids is actually red. So it's not surprising to me to see this turn red when he's talking about stripping the atoms, attacking it on an atomic level. So, hey, it checks out.
I then let it cool down to room temperature, and what I had to do next was turn all of this chloroauric acid back into metallic gold. At first, it might not make much sense why I just
Run the
dissolved it
reaction
all,
backwards.
only to immediately bring it back, but it'll all make sense in a few minutes. With that being said, I then just grabbed the beaker and started walking over to my other fume hood.
Oh boy. That's expensive. I feel bad. No.
Oh no.
Okay, that was actually just a beaker full of water and food coloring, and what I really did was pour it all into a bunch of extra water.
You tricked us.
I also washed the beaker a few times with some more water to make sure that there was absolutely no gold left behind. Then after that, I
Had me
stirred it
full.
around to make sure that it was all fully mixed, and when I felt that I was ready,
Like the
I
use of the
dumped
red
in a
spoon.
concentrated solution of potassium metabisulfite. This caused the
There we
entire
go.
thing to quickly turn brown and to heat up a lot, And I was
It's more
really
black.
happy to
Well, at least
see
on
this.
camera it does. It might
This
look brown in
because it
person.
meant that the potassium metabisulfite was working and that it was reducing all of the gold in the chloroauric acid back to its metallic form.
I'm not going to get tired of that.
The very important part, though, was that it wasn't all just coming back as a large chunk or something, and it was instead crashing out as a superfine powder. So, by just dissolving the bar and bringing it back, I had effectively pulverized it to a dust, and again, this was way better and easier than anything I ever could have done manually.
And that makes perfect sense that it's going to come back as a powder, because, again, he took it apart at a really small, again, at the atomic level, using that chemical reaction. So it's not going to come back as one big chunk. I mean, I guess it's technically possible, but the probability of that happening is so insignificantly low that might as well just say it's impossible. It's easier to explain. But it's a bit like when you shatter that beaker and you put it back together again, you could probably make a little mosaic of, you know, gluing all that beaker stuff back together, like on the ground, but it's going to be really hard to actually make it back into a beaker.
Over the next 30 minutes, pretty much all of it sank to the bottom, but there was still a small amount of it floating around. So I decided to leave it overnight, and when I came back to it the next day, it was completely clear. I was now able to get rid of all the water, and I just quickly poured it out into another container. I was also very careful to not lose any of the gold,
like dirt.
And when it eventually looked like there was almost no water left, I transferred it all to a small beaker. I then poured in some boiling distilled water.
Now it looks like the gold dirt that you see the old-timey prospectors have when they're panning for gold in the little streams in the Old West. It's like we're seeing all the different phases of regular gold before we get to purple gold. I like this process.
And I turned on the hot plate, and I let it sit there for several minutes. I was doing this to get rid of any residual potassium metabisulfite and other side products, and after that, I did it a few times with hot hydrochloric acid. This would help get rid of any trace impurities of other metals that might be there, and when I felt that it looked good, I washed it a few more times with hot water. What I had now should have been some super nice and clean gold, and all I had to do next was dry it, so I cranked up the heating on the hot plate, and I waited for all the water to disappear. This ended up taking over an hour, which was way longer than I expected, but when it was eventually done,
things always seem to take longer than you expect when it comes like that.
I had some nice and crispy powdered gold. When I weighed it, it was also 99.99 grams, and this meant that I had only lost 0.01 grams in this entire process.
Now it looks like the little rub you put on your chicken before you fry it.
However, considering that the original bar was only 99.99% pure, it was very possible that this small amount was actually just some impurity, and that what I had now was more pure than it was before. But anyway, at this point, all of the gold was ready to go, and the only other thing that I needed was some aluminum, and I bought this bag of it from eBay. It was supposed to be 99.995% pure, and it was the absolute highest purity that I was able to find. It also came as a bunch of small pellets, which I felt would make it easy to measure out, and now it was finally time to try and make some purple gold.
Almost looks like aluminum, looks kind of like the aluminum cladding you see for nuclear fuel pellets, though these are going to be even smaller than those, but not a whole lot bigger. It's crazy, though, how a little pistachio-sized item contains more energy than a ton of coal.
So I carefully measured out 4.95 grams of the gold, which was really easy to do in its powder form, and I added it to a small crucible. Normally, I also would have added something called borax, which would both help the gold melt and prevent it from sticking to the dish, but I unfortunately couldn't do that here.
Technically, borax could actually be used to shut down a reactor, since boron has a higher chance of absorbing neutrons than uranium or plutonium, for that matter. So sprinkle a little household cleaner into the reactor that could shut it down, assuming it could survive the hellish high pressures and temperatures. But boric acid is actually used to control reactor power by that same logic. Think of it as liquid control rods. but I guess you could have powdered control rods.
because it would react with the aluminum. Either way, I then just started blasting it with a blowtorch.
That's another reason why aluminum could be used as cladding, but it's less resilient, and it has been in the past, but it's less resilient than zirconium alloys. Aluminum's just more reactive, whereas zircaloy, you need extremely high temperatures, even higher than operating temperatures in a nuclear power plant for it to cause reactions.
And very quickly, the top of it turned red hot,
That's cool.
and I could slowly see some of it starting to melt. As I kept heating it, it was also slowly shrinking, and about 30 seconds later, I was left with two separate blobs, which eventually combined to form a nice little bead. I then kept blasting it just to get it as hot as possible, and when it was red hot, I dumped in exactly 1.61 grams of the aluminum metal.
Technically, this is a form of fusion, just melting and combining. It's a form of fusion. So when people talk about, hey, finally achieving fusion, or I see this mainly in a lot of works of fiction, like even in Star Wars referring to fusion as a power source, but it involves super heavy elements. Well, they can't possibly be talking about nuclear fusion, but it could involve melting or some combination of things in order to make whatever crazy shielding or armor technology they have. Just something that gets thrown up a lot.
The ones that were touching the gold almost immediately melted and combined with it, but it looked like the others needed a bit more convincing. However, even after making them red
further
hot,
away from your
they
heat
still
source.
weren't melting, and this was because the thin oxide layer that naturally forms around aluminum was holding in the liquid metal. So to actually get it to mix, I was going to have to poke at it a bit, and I was happy to see that it all easily combined together.
What's interesting is when people say, uranium, so talking about oxides, when people talk about uranium fuel pellets, it's actually a uranium oxide. That's actually where this black stuff comes from on these uranium fuel pellets that you see when if you were to actually cut open a nuclear fuel assembly. Can't say I recommend doing that to spent fuel because you're going to release fission products. That's the reason why it's protected in the super durable zircaloy cladding. Compared to regular uranium, which just looks like any other ordinary, boring, shiny metal. It is toxic, though. Radiation's not really the biggest hazard. It's just the same toxicity that you'd see in things like lead. So please don't huff it.
What I was more happy to see, though, was that below all of the crusty
Look at that little
oxides
shiny
on the
stuff
top,
in there.
it looked like there was a nice and free-flowing liquid.
It's so gooey.
I was also kind of surprised to see this, because there were at least a few comments that I read online which said that doing this in the presence of air would turn the entire thing into a horrible oxidized mess.
Okay.
However, it wasn't nearly as reactive as I initially thought, and it definitely seemed like it could be possible to pour this
Maybe it's
into a
because
mold
it's such
or
a high
something.
purity.
With that being said,
Those other people might have ran into issues with the impurities causing the thing to become more brittle. Because gold by itself is super malleable. It's just the impurities. And I guess when we get to the purple gold, maybe it's kind of like the combination of the impurities mixed with the gold and the aluminum that made it even more brittle than what purple gold is allegedly going to be.
I now theoretically had a mixture of 81% gold and 19% aluminum,
Okay.
except it wasn't even remotely purple, and this was because it was still way too hot. It was also still a liquid.
Yeah, you don't see
and to
purple
get
in
it
too
to
many
turn
things that are
purple,
hot.
I was
except for
going to have
fire.
to let it cool down. As this happened, it was supposed to slowly crystallize as an alloy, where most of it had the
Look at
chemical
that.
formula AuAl2, which is the form that has a really nice purple color. According to the patent, though, by skewing the gold content slightly higher than the typical 78.5%, it would push a bunch of it towards a gamma-phase gold aluminum structure.
Just to be clear, we're talking strictly about crystalline structures and lattices in materials here. Gamma phase, nothing to do with gamma radiation. Now, that isn't to say something that's a gamma source can also be gamma phase. It's just talking about something different. So, things like this, whether it's a face-centered cube or a body-centered cube.
I honestly still don't entirely know what that means, and I've had a very hard time finding any good info about it, But the important part
Yeah, gold and
was that it was supposed to make the alloy a lot stronger. When it did eventually get...
So mainly when I think of gamma phase, I'm thinking of like the iron carbon structure in steel. And usually gamma, so I can't say I'm an expert on material science, but my understanding of it is gamma is off, those structures come from things that are that are high temperature. So you will see things like that in piping applications, in power plants. And with the added density, yeah, I guess a gamma phase, on average, a gamma phase might be better at shielding from gamma radiation, but don't take that comment too seriously.
To room temperature, though, it sadly still wasn't purple because it was covered in a bunch of blue oxidized junk. If there were actually any purple gold, it was all hidden inside, and to see if it were there, I was first going to have to get it out of the crucible. So I just carefully poked at it with a metal spatula, and even without any borax, it was surprisingly easy to remove.
There you
what
go.
I had now
was
a super crusty and ugly piece of metal, and to see if I had actually made any purple gold, all I had to do was break it open. I also figured that this would be pretty easy considering how weak and brittle even this stronger stuff was supposed to be, so I just tried snapping it in half. However, it turned out to be a lot tougher than I expected, and it really didn't feel like I was even close to breaking it. So instead, I decided to just quickly kill it with a hammer, and I kind of assumed that it would easily shatter. But again, that apparently wasn't the case.
Slough coming off it.
I mean, I didn't exactly hit it super hard, but still, it definitely didn't seem like it was as brittle as glass or porcelain.
No.
And all of that gamma phase stuff appeared to be working. But anyway, I then just kept hitting it, each time doing it a bit harder. And when it did eventually break, I was really happy with what I saw. Inside of it was a bunch of beautiful purple gold, and the color of it almost seemed unnatural. What I thought was kind of odd, though, was that it wasn't quite the purple that I was expecting, and it seemed like it was a lot pinker than the jewelry I'd seen online. This made me think that...
That could just be as simple as some jewelry in particular a lot of times just looks different when you take a picture of it versus when you see it in person. It even looks a little bit more purple to me just looking at his video because he did it in a camera. It's fascinating how little differences like that, which is technically a difference in how different radiation detectors work, because these are all visible light radiation detectors, eyeballs and cameras.
Maybe I'd chosen a bad recipe or something, but when I checked the patent, it actually said that it was supposed to be a pinkish purple. It also said the same thing for all of the other recipes, and again, considering that this was the patent that the Liwa stuff was based on, I trusted that it was probably good. I also started thinking that maybe the darker color only came out later on in the process, or when it was being polished or something, and I decided to just keep going. So now, assuming that this recipe was good, what I had to do next was somehow figure out how to go from just making a bunch of crusty crap to a nice and shiny ring. This was going to be a lot of work, though, and just thinking about all of the different things that I was going to have to test kind of overwhelmed me, and this made me feel that the only way to move forward was to just take the process step by step.
That's how you break down anything complicated, but this is a huge undertaking, and it's crazy that he's doing so good at something like this with things that he's never done before, things that aren't very well documented, and he explains it in such a compelling way that I don't know if some people are watching this and just following along with their own step-by-step.
This way, I wouldn't break my brain, and I would only have to focus on one major problem at a time.
Don't want your brain's looking like that.
Right now, I felt that the biggest issue was the oxides. This is because they were clearly making everything a huge mess, and if I even wanted a remote chance of making anything nice, I was definitely going to have to get rid of them. To do this, there was also only one real way, and I was going to have to somehow stop the aluminum from reacting with oxygen in the air. So I went online looking for some ideas, and after searching for a long time, I was only able to find 2 decent suggestions.
I like the way he Google searches.
The first was to buy a super expensive and specialized inert atmosphere casting machine, and the second one was to basically custom build something that was equivalent.
What even is this thing? All right, I mean, okay, yeah, it says he stuck it into an AI, but that is awesome.
However, I really didn't feel like it had to be that complicated or expensive, and after thinking about it for a while, I came up with an idea that I thought was relatively simple. I figured that all I had to do was use this small tabletop furnace that I already owned, and to load in one of my smallest crucibles. Then after that, I just lowered in some stainless steel tubing that I'd gotten for free, and I'd quickly bent it to fit around the furnace. What was important, though, was that at the other end of this tubing, it was connected to a tank filled with inert argon gas that I'd gotten from a local welding shop, and that was basically it. What I had now was just a regular furnace with the ability to shoot some argon into it, and I really felt that it was going to work. There was only one way to find out, though, so I quickly added the gold, started a steady flow of argon, and I set the furnace to 2200 Fahrenheit, which is about 1100 Celsius.
Yep.
Over the next 15 minutes, it then slowly heated up, and the gold powder slowly shrank, except it was looking like it was having some trouble melting with the top open, so I covered it with some KO wool. After that, it only took a few minutes to have a nice little blob of gold at the bottom, and now I could add the aluminum. This time, though, I decided to use some much larger pieces of it, which weren't quite as pure, but I was hoping that they would liquefy a lot more easily than the smaller ones. To load it in, I just carefully dropped in the first piece, and I was very happy to see that it all quickly combined with the gold. I then added the rest of the aluminum, which also quickly got...
Yeah, melting point of aluminum is about half that temperature, so not surprised it did not last very long.
Got sucked up, and at this point, it was already looking way better than the first attempt. What I was especially excited...
That's another reason, by the way, why you don't moved away from using aluminum as a cladding, at least by itself, because, yeah, it just doesn't resist high temperatures very well.
About was that it looked like there were barely any oxides, and this meant that the argon was doing a decent job. This was also really impressive considering that the aluminum was red hot and that it was way more reactive than normal liquid aluminum. But anyway, what I had now was some nice and relatively oxide-free purple gold, and what I had to do next was try and pour it. In theory, it probably would have been a good idea to protect it from air while I did that as well.
Sure.
And I did consider putting together some sort of specialized setup. However, instead, I decided to go with the very sophisticated method of just going as fast as possible.
Yeah, there you go.
So I just quickly got rid of the argon line.
Go fast so the oxygen doesn't have time to do its reaction. That is an approach to do things as fast as possible. At least within the nuclear industry, that's not one that's very highly regarded. It's definitely the go slow to go fast mindset that shows up, but let's see what happens.
Pulled the crucible out of the furnace and tried pouring it out onto a preheated graphite mold. As I did this, I was really hoping to see a nice stream of red-hot metal, but nothing was coming out.
That's what I was expecting, too.
And it didn't even work when I tilted it completely upside down.
It stuck to the bottom?
At first, I was kind of confused, but then I realized that all of the purple gold had just frozen in the crucible. Apparently, just a few seconds was enough for it to cool down below its melting point, and I was clearly going to have to get it as hot as possible. So I just put it back in the furnace, dropped in the argon line, and covered the top, and I left it there
Crank it up
until the entire thing was bright red. I then again attempted to go as fast as possible, and it was still a bit stubborn, but I was actually able to pour it out.
Just one slow. Oh, look how fast that goes. The only sad part
was that it was a complete piece of trash, and having to remelt it had apparently caused it to get really oxidized. This told me that I only had one real chance to pour it out, which wasn't ideal, but at least now,
never ideal.
I knew exactly what to do.
Well, I think that's going to end part one. We'll find out what he exactly knows to do in the next part of my reaction to this. I've really enjoyed this one. I can tell how NileRed's just gotten better and better over time. And I still just love the attitude. Unsure process, not a jewelry person, but I still think I can do this. And thus far, him already seeing some of the purple in that flaky stuff he made earlier, I think it's going to be really, really cool. Thank you very much for watching. I'll see you next time.